All right, happy Monday, everybody. It's baked potato jam time. No, it's not baked potato with jam. It's not even jam made out of baked potatoes. Alex is running a Godot jam. We're going to talk about rain marching tonight, and feel free to work along. And if you enjoy it, he'll be doing this again March 16th, and you'll be welcome to come out to his office, all right, his apartment, and enjoy baked potatoes while you work on games in Godot. So had a lot of fun of late. We had the Transformer conference went really well. Many of us just had Next Fest. Definitely make sure you wish list um, uh, Banana of Doom from Timothy Johnson, and of course Machiavelli the Prince. The more of you who wish list these, the better. It's the last day of Steam Next Fest right now. It's actually probably officially over, but you can still wish list them. All right, we got SimFest this weekend. Great opportunity for game dev panels with Michelle Menard keynoting. Dragon Snack Games. Learn what she has been up to since her days on working on Civilization. We'll also be having the Atlanta Sci-Fi Fantasy Expo with Siege panels. That'll be the 14th to 15th, so make sure you join us. You're hearing some dings in the background. That's the way people join us in our Discord. That's right. If you are a GGDA member, you can join us in the Discord to take part in this. Our members get to ask questions. Thankfully, they're all very polite. We'll only ask them when there's a good opportunity to do so. The rest of you in YouTube, I will be glad to relay your questions, but you don't get the exact one-on-one help of the GGA members in the Discord do. But please do ask your questions here. If you can't see the screen well, let me know. It's looking good to me, but then I've got big eyes. I don't know. I got something like that. If you cannot see well, let us know. I think it looks pretty nice, but let us know if you can't see, if you can't hear, anything like that. And with that, I'm going to turn it over to our Potato Meister du jour. That's right. Usually it's the team that makes all the potato games, Masterworks, and things like that, the Fanaticus team. But today, it is Alex. Alex, why don't you go ahead and tell us something about yourself and then tell us what we're going to be doing today?
I feel like that was a much more wonderful intro than I deserve. So thank you, Andrew, for that. We're going to be doing Ray Marching in Godot. And I hope that nobody's turned off by either topic, because if you're just here for tech art, or if you're just here for Ray Marching, it doesn't really matter what engine you're in. A lot of this code kind of works everywhere. And if you're only loosely interested in remarching or not really at all, a lot of this stuff applies to a lot of other things in tech art. And if you know nothing about tech art, I hope this kind of encourages you to dive in. And I figured I'd kind of lead off with a disclaimer of the premise of how I operate, at least in terms of these workshops, is that I don't know what I'm doing. I started learning programming really recently, and so I'll be kind of crashing for the next hour and a half, tumbling down the mountain trying to figure stuff out. So you might see or will see errors in my code. I was catching major problems in it until literally a couple hours ago. So don't treat it as a reference, but I am trying to at least make it educational, at least for people who've never kind of touched remarching. And then this is kind of what we're headed toward, is this quad with this kind of weirdly 2D shader on it. In terms of like what remarching is, we're kind of used to the process that's called rasterization, and that's where everything is pretty much defined in the form of a mesh. And I'll pop open Blender. Let me add a mesh. And oops, let's scale this up. So this is kind of what we're used to in terms of how we see shapes and game design as these meshes. And remarching doesn't work that way. It defines its shapes just using mathematical functions. and it defines the way the rays move just using mathematical functions. And that can let you do a lot of really weird and fun things. For one, it lets you define shapes into infinity. Like if you were to zoom in on this mesh, you know you're always going to see the angles eventually. And you don't really have that issue with ray marching, although you can in another form. And then you can also do things like fog effects and smoke. So if you're doing like a smoke grenade in a first-person shooter, and you really wanted it to look really realistic, you'd have potentially a ray marching shader. Or if you hated the cloud box that kind of comes shipped with a lot of game engines, or the regular fog effects, you could dip into ray marching. But for now, we're just going to make basic shapes and toss them together in a scene and try to get a sense of how a ray marching function works. Or at least I'll do my best before my brain shuts down. I have been working since this morning at my day job, so but I felt like uh, maybe it's a good motivation, because that's kind of how game design, I think, goes, and learning this stuff goes, is all day, and you got to like knock an hour out in the evening to move a project forward. So that's the spirit of what we're doing. Me. Go ahead and get the project going. So I hope, for my own sanity, I'm going to use the same project I've been using, but I will use a new scene. So if you've already got a project started, great. If you haven't, go ahead and click the buttons. I think what most people do is that they just watch at first, and then they like take the code and play with it later. So I'm kind of assume that that's what most people are doing and organize around that. So I'll do a new scene. And I like having two views open. And I'll define the root node, which is just a 3D scene that puts us in 3D space in Godot to add other shapes. And then I always mix up whether it's Control A or Shift A to add things, and it's Control A. Great. Because I know it's Shift A in Blender, and so if you're used to Blender, it's Control. So Mesh Instance 3D is going to be our first object that we start out with, because we want a quad. I'll stick that Mesh Instance 3D in there. And we get nothing, at least at first. We can't see an object yet. And that's because we have to go to this box in the inspector column. And I hope you can see my mouse, as I probably should have picked a bigger mouse for this. But up in this right handish corner, we'll select a quad. Then we need to give that quad a shader so that we can start editing the code. So surface material override, it has a drop down. You'll click shader material. And then in the Godot spirit is often just keep clicking until it gives you the opportunity to like do the thing that you want. So we'll click again. And then we have yet another drop down to click to create our actual shader. We'll do new shader, live stream, call it what you want, of course, and create. Then we have to find it, hopefully, So this is our file system here on the left. And then this window is our shader editor panel, or at least it is for now. So when I double click into that, I'm going to open my actual shader code. And it gives us a couple different places to work. A vertex shader, it gives us a fragment shader, as well as a light function. We're not going to work on the light function. We're just going to do most of our work inside of the fragment area. Fragments, I guess you could just kind of think of those as pixels for now if you wanted to dive into like the theory of what a fragment is. I'm sure there's lots of YouTube videos on that. And then vertex shaders would be if we wanted to like move the vertices around, and there's only 4 vertices in this quad, and that's not what we're invested in. Yeah, we want to project an image onto this quad. So I'm going to do this differently than how I did it last time I taught this, and I'm going to paste in the entire shader that is the end goal, and then I'm just going to comment it all out. And then as I uncomment it to bring the code back into being, I'll try to explain each piece and what it's doing. So I'm going to paste in the shader that is the final destination. Looks like this. And then I'm going to start commenting away everything. I need to find the fragment shader specifically because I want to get rid of that. Da, da, da. So Control K, after I've highlighted everything, we'll just make everything disappear. And these are various functions that I'll explain in a bit. So I'm going to nuke these as well. It'll start out just saying shader type spatial. This line render mode unshaded is something that you're going to have to add for a ray marched shader, at least for now. Otherwise, Godot is going to try to shade this object with, shadows and other things that are happening in the scene. And we want our ray marching shader to operate independently of everything else. And just to kind of give a sense, I'm going to pop open. Let's go over to the fragment shader and talk quickly about UVs. This is Alex coding live while tired, and so I don't know if this will do what I want it to do, but we'll find out. Yeah, it did. Yay. I'll do this as a quick kind of sanity check. If you don't know what UVs are, UV doesn't actually mean anything. I used to think that UV meant something, and it's just a replacement for X and Y. And so in this space, I'm going to actually pull open Blender so I can draw on a plane. Go away, icosphere. Go away, cube. I'm going to do Shift A and add a plane. I'm going to rotate it on the X axis. Try to get 90 degrees. What's that? And I'll zoom in. And then I'm going to go into the annotate section. I'm going to try to annotate everything I'm doing in the world of the shader. And I'll often do that at home in Blender so that I don't go crazy trying to understand the math. And I'll do it more next time when I talk about how to derive the field of view for a ray marched shader. And this UV part might be really boring if you're familiar with UVs already, but I don't want to assume anything. And then I'm going to change my annotate to be on the surface. That's this window, this drop down up and to the left. Is this way too tiny, by the way, for people to see, Andrew? Okay. I'll just have to take it on. It's not a Blender class; it is a Godot class, so I won't, fight with Blender just yet. So a quad, and really everything, has UV coordinates, and everything is divided into triangles. So let's see if I can. I have a double monitor set up, so my I can't draw straight lines on my tablet right now. So that's what we got. So you've got a two triangle setup on a quad under the hood, and you've got this U-axis and this V-axis going up and down, and they have coordinates. So this vertex is at 0, 1. Sorry, 0, 0. This vertex, like kind of following the x-axis in math and grade school would be 1, 0. This one would be 1, 1. And then this would be 0, 1. And the first thing that you kind of notice about this is that in math class, our origin is usually in the center, right? There's usually like a y-axis there and an x-axis there, and then that's how we do all of the like math that we're used to. We want to be able to have that level of access with our UV shader, when we're coding, and we want to be able to have a sense of what we're doing when we're doing the math of the ray marcher. So we're going to do something called converting it to normalized device coordinates. We want that origin to be centered, and then we want this to be -1. We want this to be +1. We want this to be +1. And we want this to be -1. Sometimes these are inverted. If you're working in a 2D game, you probably already or may already know that the y-axis can get flipped. And we can flip back over to Godot. And here I've mapped, we have an RGB coordinate. So albedo just means color. And vec3 is the 3 color components of your monitor. So you've got the red component, the green component, and the blue component. And for at that 0, 0 place that I've pointed out in Blender, I'm going to try to put that a little smaller. We know 0 and 0 should come out black because there's no colors assigned to it. And so that's what we find. We find a little piece of black on the top left. And then we should expect bright red in the top right because that R component of the vector is 1, which is 100% in this context. And there's no green added. And then we see the same thing with green added into the v/y component of the vector, and then they get blended at 1, 1 on the bottom right. And it can be easy to kind of forget that, and when you're working with shaders, you don't have the benefit of a print function. Like normally when you're programming, you don't know what's happening, so you type print, and then you type in the variable that you're trying to figure out, and you don't really get that here. Like this is your print. So you're kind of constantly trying to output something understandable to the shader in order to understand and figure out what's happening. So get rid of my drawing pad for now. As I said earlier, we want to center that UV axis. So I'll go ahead and get rid of this. Just comment it out for now. And here I've done two things in one line of code. I've created a new variable to hold the kind of putative UVs. And I kind of actually don't like the way that I've done that. So I'm going to make it a little simpler to follow. And I'll say vec2 green UV equals UV. Bam. And then I'm going to bring this back from the dead. And then rather than use, see how this UV is capitalized, and then we've got this lowercase screen UV. So I've taken the UV that is a, I'm blanking on the word. The variables that Godot just gives you, built-ins. So you have what are called built-ins, which are variables that you just always have access to when you're working in the shader. And you always have access to this built-in, which is the uppercase UV, just like you have access to something called time. And there's a whole list of built-ins that you can search for with the Godot documentation. So I want to start moving around these UVs. So the first step is assigning them to this variable. And now I want to start changing it around. And I want to make sure this variable is doing the job. So I will replace that with that. And I end up with the same look. If I was to put this in the blue function, which we'll just try out, we start kind of changing our colors around. So I'll often do little sanity checks like that to make sure things I'm doing are having an impact. So now I want to center that origin. So if I go back into Blender, if I take all of these points and I multiply them by 2 and I subtract 1, I'll end up with the origin here. So if you were at 0, 0, and you multiply that by 0, then you get to that -1 number, and you'll get up 1, 1 down below. So it's easier if I just show you. So I'll knock that out now. And I'll drag this down. And see, that centers our origin to the center. And so now everything up and to the left is below 0, so it ends up black. And correction that's normally made here is for the viewport size, where people will correct for the aspect ratio. I'm not going to do that today because all of the lens corrections I want to make next time, because that gets kind of real messy real fast. Let's go ahead and start declaring some other variables that matter for our ray marcher. And the first is the origin of the rays, which is where our rays start. And the second is going to be our, camera position. And the reason this broke, so you'll notice that everything went gray, even though this line isn't really doing anything to change the color. Like, you're like, well, why should this breaking do anything? That is just what happens with shaders, at least with Godot shaders. It's your kind of tell that you've got some kind of coding error in there. So that's a warning sign. So I can go ahead and get rid of that error if I clean up my camera position up above. Where did I stick it? Here. And then my camera position, I've put it 0, 0, 3. And what I'm also noticing is that that should have fixed the gray, but didn't. I don't know if I have any programmers in the audience to save me. I probably don't, so I'm probably on my own. Oh, I've declared this twice. Yeah. Get ready. And when I said I declared it twice, you have to declare each variable you use, and you can only do that once. At this point, I want to start matching up what I'm doing in my ray marcher with what's happening in the scene. And I've noticed that when people talk about ray marching, they'll talk about reality. And when they say reality, they mean what's happening in the game engine. Like, this is reality. And then the fiction is what's happening in the shader. So this black, red, pink, blue, like that's the fiction. And then all of the space around us is the reality. So we want to start matching reality up to the ray marcher. So I'm going to add with Control a camera. And there's my camera. It starts at the origin at 0, 0, 0. And in my code, I've put that camera at 0, 0, 3, which is going to march it in that direction by about 3 meters. It looks like I've got snapping on unintentionally, but that works for now. And I'm going to check my camera's position in the inspector to make sure it is where I expect it to be. Something to know is that Godot is, I think, what's called a right-handed coordinate system. I get really confused by the left-hand, right-hand mnemonic. I know that it was invented to be helpful, and I know a lot of people must find it helpful. I find it confusing. But you're looking down the negative z-axis. So I've moved the camera positive z 3 units, and it's looking towards negative z. And then if you want to get a little help from your gizmo, the brightly illuminated parts of your gizmo are corresponding to the positive and the negative. So this is positive z, positive y, positive x. And I think that tends to be the gizmos on other apps too, I assume. So I'm going to pop on down to the code again. And then next part, we have the ray direction variable. And it's mad because I mentioned the camera focal length that I declared up above, but it's commented out. So I'll bring that out of the commenting purgatory. The camera focal length, this part is a real like brain bender, and I'm gonna derive it all next week because there's a formula that you can use so that this number can line up with whatever the focal length is of your camera. So this is an arbitrary unit when you're ray marching. It's just starts at 1 and can be a lot of different things. Field of view is where you'll see it in degrees in Godot. So here it's set to 75 degrees, which I just so happen to know is about 1.3 for ray marching. And then if you're in Blender, if you hit the N button, and I know this is small and I apologize, but there's a view tab, I promise. And within the view tab, at the very top, it says focal length. And that is in millimeters, and that I believe is to line up with what you would experience with a real life camera. So you have 3 different ways of thinking of focal length, and if you add the fact that sometimes it's not degrees, it's radians, then you've even complicated it further. Whenever you're sculpting, by the way, you usually want to knock this up pretty high. And I'm going to do that now. And the focal length, you could think of it as how much you're zoomed in. If you're using a real life camera, you know that the closer in you are to something, the more distorted it is. And if you are very far away from your subject and you're zoomed in really heavily, you have a much flatter and much less distorted look, which is why, sculptors usually will crank their focal length really high because they don't want that distortion. But the ray marchers will often have it pretty low to kind of give the effects an in-your-face look. And back to the party. So we declare distance to surface. This is where the party starts. And it's going to get mad because I declare these variables up top. But I'm going to try to just get this window. Oh, Godot's latest version introduced the ability to create windows, which is nice, if I can find it. Yeah, here it is. So this little triple dot make floating allows you to, break your code out, which is nice for streaming and for ray marching, because these things can get pretty intense. Get back to Blender. And I'm going to recreate my scene a little bit. And this plane, we'll hide it for now. Oh, that didn't get rid of my notes. We'll hide you. I'll start with the ray origin. So this is going to be our camera. And we're going to visualize our camera for now with a sphere. And I'm going to make it small. And again, I'm lining up everything perfectly in Blender too. So this is -3 meters out. And our object that we're going to be looking at is ultimately going to start with a sphere. So I'll create another sphere. And that sphere is going to have a radius of 0.5 because that first sphere had a radius of 1 meter and that was on the big side and we don't want that. And then I want a plane that I can draw on so that I can explain everything. And when I scaled that sphere, I hit S and then I typed in 0.5 and hit enter. So Shift A, plane, rotating around the y-axis, 90 degrees, fix it there. Then I'm going to make it big so I can draw on it. And then I'll add another annotation. So you have these layers of annotations, which is really nice. I annotate a lot when I'm blendering. Ray marchers. All right, I am hoping that this will pan out. I need to mute my phone, I apologize. So this first part, if you're used to Python, is a for loop. And I've now gotten used to every time I learn about a new language, I forget the former ones. I've forgotten already how to write a for loop in Python, but I'll walk through what this is doing. So this is starting, array is marched forward with a series of steps. And this, for our purposes, we're only going to march at 20 steps, but that number is arbitrary. And so this is saying you start with that step at 0, which is pretty common when you're doing a for loop. And then you're going to march that step upward. You're going to iterate all the way up until you hit that max march steps figure. In this case, it'll be 20. Behind the scenes, that number is 19, but it's starting at 0, so you still functionally get 20 steps. And then this step plus plus, that's shorthand to mean that it's increased by 1 every time it goes through the for loop. So this is a pretty conventional way of just repeating some instruction some fixed number of times. In this case, 20 times at most. The first thing it defines is where we are in space, which is the current position equals the ray origin plus the ray direction times the total distance. And then it takes this It does a distance to surface function, and then this OR function. So let me flip over to Blender and try to like explain how to like wrap your head around this. So let's just say arbitrarily we've already shot the ray for some amount of space and time, and it's here. And let's say we shot it at a what is it, 45-degree angle. And we're working in 2D space for now, so we're just kind of assuming 2D space. Oh gosh, I cannot write with a double monitor setup. I apologize. So this first current position, so we want to like find out where are we right now. And we find that out by taking the ray origin, which is that negative, or which is that, in this case, -3, 0, if we're thinking of it in X and Y terms. Plus, and then you get a normalized coordinate, which is the ray direction. And this would be that vector would be the Pythagorean theorem, right? Which would end up being the square root of 2, I think. So you're like, what is the square root of 2? Anybody in the audience want to help me out? I think I've primarily got YouTubers, so I think I'm on my own and I'll just proceed accordingly. We'll just assume it's roughly around 0.6. So you've got this kind of 0.6 vector.
It's
where your
1.41.
1.41?
Yeah.
Hold on, so a normalized vector still has to come out to 1. Yeah, this is where my brain shatters.
You're probably doing square root of 2 over 2. That's the one you're looking for, right?
Yeah, I think so. Yeah, what's the square root of 1? That would be
1.
No, fuck. And I swore I was not going to use 4-letter words, and we saw how long that lasted, so I'm going to pull up the calculator. I'm just gonna survive it. So
I think the number you're looking is 0.7.
yeah, and why is that? Why is it 0.7?
Well, if you do the cosine of 45 times 1, because the vector is 1, and that will give you the opposite side. Sine of 45 times 1 also give you the adjacent side, or the other way around, but it gives you the square root of 2 over 2.
Well, thank you for bailing me out. What we ultimately are going for, because in a way this is not the most important part of our project, we want that total distance to be something that we can multiply and still result in the new vector. So this kind of arbitrary normalized thing times, say this is 3 meters. We want this multiplied by 3 to give us this coordinate. And that's all that's happening with this function that I clearly need more hours of sleep to explain.
Why is it 45 degrees again?
So that's just arbitrary. It really, you're going to be calculating this for every pixel that is rendered of the shader.
Oh, okay.
And it's actually in 3D space, right? So this, let me add another plane, rotate it around X, 90 degrees, get rid of this first plane. What's really happening, get ourselves a new thing, is these rays are getting shot towards every place on the shader for every frame. So that's why our UVs are going to matter and why they matter in the beginning. And that's, maybe I should just go ahead and pull up quickly the code for the focal length. Because the ray direction is defined by normalizing the vec3, in which the first two coordinates are your UVs, and then your third coordinate is that arbitrary focal length. That's down the negative z-axis. So just to kind of give a sense of this, if we were like shooting our ray, we know this is 0. Sorry, this is -1, 0 right here, right? Hopefully we're with that party. Our focal length is going to be this span, which just so happens to be 1.3 for our purposes. And then it's going to normalize shooting that ray, you know, where this is your X, your coordinate, your Y coordinate, and this is your Z coordinate. And that's how you get your direction. And if you wanted to just skip ahead to next week into how you, like, you know, get your field of view out of that, it becomes finding the tan, you know, because you know your opposite and your adjacent, you know your theta. But I promised I wouldn't get into focal length, so I'm gonna keep going. Oops. So that's how we know where we are in space now. The next step is this get seen distance function. And this is kind of the meat and potatoes of a lot of remarched shaders, which is that they use something called sphere tracing. Pop this back up. So with ray marching, you are marching your ray forward, and eventually you'll get to the part where you calculate the normals and the lighting and how it interacts with the sphere once it touches the sphere. But for now, you need to know how safely or how far can you safely march that ray along its path. And we have a mathematical function that we use to do that, which is the distance function. And for the sphere, its length length p minus r. And I'll get into this in a minute. But we use a mathematical function that tells us exactly how far this point is from this sphere. And that's really great for this ray that shoots directly towards the sphere and hits the closest point on the sphere. And so that ray will only take one step to hit it. Every other ray will fail to do that because the SDF functions as a circle, right? So for every other ray, this is how far you can travel. Because every other ray doesn't know anything except for what the closest distance to the sphere is. So other rays will travel, and hit here. And then they'll do that same call to find the distance. And they'll do that same circle again. You know, how close can I travel before I hit it? Boom. And boom. And so you can quickly see why ray marching can get extremely expensive, because if this is happening on every pixel and it's happening like 20 or more times, that's a whole lot of math per pixel per frame, especially if you start thinking about adding lights and shadows and normals and stuff like that. So I'm going to pop back open to the code. And here's the call that tells the ray marcher what the distance is, the safe maximum marching distance is. And I've done something weird, which is I've used variable names that make sense to me. If you go on Shader Toy and you read the shaders there, these functions are all going to have like one letter names. And that doesn't make them faster, it's just the convention. But I think when you're learning them at first, for me, it made it a lot easier to just give them names that made sense. Though I do shorten like radius to r because I'm pretty used to that. Then we get to this OR function, where if the distance to the surface is less than what we call the surface epsilon, or the total distance is greater than the max march distance, then we get out of this function. And that's going to handle two events. So I'll go ahead and address each one by one. The epsilon, remember this other ray, we could just go nuts in terms of like how close is close enough before we say hi, hit, like we've hit the object. And that's defined by the epsilon. You'll see that shortened to just E in a lot of code online. So if you just see E, that's usually what it means. I've spelled it out as surface epsilon. So that's the first break path. The second break path is if the total distance is greater than the max march distance. So I think I forgot what we set it to, but say it's like 6 meters and our ray goes this far and hits the 6 meter mark and it hasn't hit anything yet, if we know that there's no more objects after that, then we do want the function to go ahead and break there. And at that point, we decide what it does. Maybe we want it to render a background color. Or maybe we want it to be transparent, in which case we'll set the alpha to 0, 0.0. That's going to be up to you as the artist in terms of like, what do you want this to look like? The thing that I am heading toward, at least with these sessions, is to try to create a cloud surface and a volume that layers on top of an existing Godot scene. So I'm going to be setting the alpha to 0, which is probably what you're going to be doing most of the time. Like if you have a smoke grenade, like, you know, you just want the ray marcher to exist and only spit out ray marched objects and nothing else. But if you were like making a demo shader and you wanted to do something creative and weird, then of course you'd do something else with that. This last line of this ray marcher, this is where we've already calculated this, like the closest possible distance to any surface in the scene. So we add that to the distance of the next march, the next step. So that's what happens there. I'm going to start hopping back upstairs to declare some of these variables that I forgot about. So max march steps I need to bring back out of the dead. And I know we'll need these, so I'll just go ahead and bring these back. Max march steps, again, this is a way of limiting how much detail you get. Surface epsilon, how close does the ray need to be? And that max march distance, how far should the ray be going? And this could be, of course, any number depending on like the size of the scene. And I'll go ahead and bring the light in as well. And we need to start bringing in the distance function, because without the distance function, this ray marcher doesn't work. It's currently relying on the distance function. So this is a function for a sphere, and then this is a function for a box. If you saw them on, so there's a guy named Inigo Quilez, and let me pull up his website so you can see it. So that's his name. This is his website. If you just search Inigo Quilez, it'll come up. And he's got primitives and functions for lots of different shapes. These are for 2D. So let me grab his 3D functions. Let's see if I can make this big for the stream, because I know that the text needs to be large. You can see that his is a lot like cleaner and shorter than what I'm doing for a couple reasons. One, he's just using the conventional naming structure of, just P, just R. And then I'm also doing something different. I'm warning myself that P, for our purposes, is point minus origin, because we actually have to subtract location of the object before we pass in the point that we're measuring from. So anywhere that you see these functions, if you're like using whatever the code I'm using or something similar to it, you'll have to remember that, and that'll come in later, make a little bit more sense later. So we define these shapes, and then we also need a main distance function for the entire scene. And then I'm going to get rid of these top two, or these bottom two for now. So this get scene distance is where I'm going to toss all of my shapes in. And now we're getting a little bit closer to what you might see on the internet in terms of how these often look. But they package it in all kinds of ways. But here I start listing all of the objects and where they actually are. So I pass in a point, and then I warned myself that I needed to do point minus where these objects actually sit. So here with the get distance to sphere, I'm passing in the point, and then I'm subtracting the location of the object. And here the location of the object just happens to be at the origin, so it won't have any effect, but it'll matter later once we start adding objects and we want to give them locations. And then that distance to sphere function is also expecting a radius. So I'm passing in a 0.5 radius. And then I'm returning D. And if we have time, I'll get to adding other objects with a min function. Then we also need a normal function, and this part I'm actually going to skip almost entirely. But I'll talk about kind of what it's doing. I'm not going to explain how it works. I had a mentor, and he would talk about these really complex legal cases. Because sometimes you like have cases that are like 40 pages long, and they have just some really exhausting legal reasoning. And he would refer to them as just like the cases that you just get out some bourbon and sit with for a couple hours. And that's how I felt about this normal function. It's just something to kind of like sit with for a couple hours. Or maybe you just understand it right away because you're used to like finding slopes. But what the gist of what it's doing, and if you're not familiar with normals, in grade school, we often found tangents, right, of curves. And so maybe this was a tangent to this part of the line, right? And perpendicular to that tangent, if I can draw it, would be this. And that's, in a 3D object, that's functionally a normal. And why that matters, it matters for lighting, and in particular Lambertian shading, which we'll get to in a few minutes. But when you have an object, and this is the surface of the object, if the viewer is here, light source is here, it's going to be brightest where these angles are the same. That's going to be the brightest part of the object. And so it's important thus that we know what direction this object is facing. And in this case, it's facing this direction. And so we have to calculate that, and that's calculating the normal. So in this case, when our ray hits, we need to know that the sphere faces in this direction at that particular point in space so that we can shade it right. And the gist of how this works, you can drop the z variable and just work it out with x and y if you want to kind of play around with it and learn how it works. But it goes a little bit left, a little bit right, a little bit back, a little bit forward, and a little bit up, and a little bit down. And then it subtracts all of those from each other to find the slope, essentially, and the line perpendicular to it. So that's all I'm going to say about it. I didn't want to get lost in the weeds of normals. And then what I'll also say is that I included this version of the normal function because it's the easiest to like wrap your head around in terms of what it's doing. But it's not actually the ideal normal function. This normal function samples 6 different times, right? And this function is super expensive, and we don't want to do it. We want to do it as few times as we can get away with. So there's another method that you can look up that only samples 4 points rather than 6. But that's kind of harder to wrap your head around. So if you think for learning, you know, and obviously we're just doing basic shapes, start with that. Back to this party. And then we're zeroing in on the home stretch, actually. Let me see if I've got anything that I care about that I have left out. And so array has kind of 2 possibilities in terms of what happened to it. One possibility is that it eventually found a spot where it was within the epsilon. It was close enough to be under the epsilon, and then we counted it as a hit. And if that happened, this is what occurs, right? So the alpha is 1, of course, because we want to be able to see it. We want to get the surface normal, which I defined above. And then we do Lambertian shading here. This is ray marching and not Lambertian shading, and there's lots of videos about Lambertian shading, so you can totally just like pull that up anytime and read about it. But if you want to kind of mess around with it, you know, you could experiment with adding other kinds of lighting to the scene, or adding like point lights. Like this is just an omnidirectional sunlight, you know, but a point light would be interesting to add. So I'm going to pop back over to Godot because I think if I'm looking at this right, we'll be seeing a single ball. So this is, I guess, the moment of, not really the moment of truth, but oh yeah, there we go, a ball. A 2D, very 2D ball, but a ball. And to give a sense of kind of, to play around with this a little bit more, let's see if I can bring my code back in. Oops. Here I've zeroed out the alpha if it missed the scene, but say I just wanted it to be black, it's already set to be albedo 0, 0, 0 across the board. We know that that means RGB is all zeros and thus black. But if I set the alpha to 0, we should expect to see that that fills back in again. And in some cases, that'll be exactly what you're going for. And it does seem that I have time for it, so I'm gonna add another shape in. And going back to that website from Inigo, he has various functions to add and subtract and do booleans. So you can look up how to add and subtract, do booleans and other weird functions. But just basic addition is a min function. So, and it's a chain of min functions, comically. That turned out to be a box, so let's add another sphere for now. So this particular sphere, I've moved it 2 meters along that arbitrary x-axis. I haven't moved it up or down. This is our y-axis. And I've moved it away from us, which is down the z-axis. So I've moved it 3 units down the z-axis. And again, it has a radius of 0.5. And, you know, I could play with that and see what I get. Now I've got a bigger ball. And then something I want to check for is this box that I'm about to add by calling the distance to box function. It's 1 unit up, right? In theory, it's supposed to be 1. So we'll find out if that's how it plays out. And I don't think it will, because I don't think I put in the code for it. It ends up going down, which happens when we don't flip our UVs around, because as I mentioned before, it defaults to 1 being down on the y-axis. So I think I already wrote in the code to flip them, but if I didn't, I can add it back in. Yeah, here it is. So if I multiply that screen UV times the vec2, the x coordinate is 1 and the y coordinate is -1, that'll just flip that y for me. And I think for now, if you're just now learning about it, it would be a good time to just like add shapes to the function. Like first experiment with just adding more objects. So say I wanted to add another, let me find my list of objects. Where did you go? It's a bit of a struggle because my text is really big since I'm streaming. And that's my normal. Haha. And then I think another thing that's worth doing is breaking the march steps to see what impact it has. And I actually haven't done this enough myself. But let's drop it down to 2 and see what happens. And we see nothing. So as you can see, if you don't have enough steps, it never gets close enough to reach that epsilon. And something I was experimenting before, I changed the code at the last minute, like a few hours earlier today, because I was like, do I really want it like this? Go ahead and fix that before I leave. Branching that happened here. You know, I chose to branch it in this way if distance to surface is less than the surface epsilon. So this only pulls it in if you have a hit. But you could reverse it and only pull it in if it perceives a miss and then handles everything else as a hit. And that might be what you want. It might not be what you want. I think I should have just kept that code around so that I could paste it in. But know that you can flip that logic on its head and do something else entirely. I should probably start with questions because my brain is already at the shattered state of the evening. I don't even know if I'll be able to manage questions now. Do we have any thoughts?
Right. If anyone in the chat has any questions, feel free to ask them. Anyone here in our Discord have questions, go ahead and ask. I remember when my studio, when HCI started going from 2D games to 3D games, when our programmer started explaining UV coordinates to me, I said, what does this have to do with ultraviolet? He says, nothing. U is X and V is Y. It's like, what? Why isn't X X and Y Y? No, because it's 3D. So,
I'm glad I'm not the only one who thought UV meant like, because I thought like light. Oh, maybe it has something to do with light, and then it was like, no, it's just X and
the
Y.
joke that I have used and others have used is that it is called UV because it causes people to become ultraviolet when they try to understand it.
Oh, I hope I made it easier. I don't know. Someone I should call out before I like. If you want to learn about tech art and you want to like actually legitimately good class, there's an instructor named Freya Holmer. Let me pull up her YouTube class on shaders. This is amazing, and it's, I think, about 12 hours. It's divided up into 3 parts, and it goes through just all of the things, just beginner all the way out. She does work in Unity, and again, like it really doesn't matter if you're in Unity or Unreal or Godot, like shaders are shaders. So I can't recommend this enough in terms of a starting point if you're like just totally overwhelmed by UVs and shaders and the basics of like shader code. So start here if like any of this is like mind blowing. Sorry, back to you, Andrew.
All right, Tyler and Elliot, you've got first dibs on asking questions since you're in the Discord.
So UV is always between 0 and 1, the original UV. Or like if you have like a bigger square, it's gonna be between 0 and 2 and for U and V. Like I remember you showed that it was from 0 to 1 originally.
So on a question I think was is it between 0 and 2 or sorry,
Oh yeah,
ask the
like
question
you
again?
did it originally from 0 to 1. Like that's just how you said it was
Mhm.
what Godot gave to you. Is it always gonna be between 0 and 1, or like if you have a bigger figure, it's gonna be 2, or is it kind of like normalized that it's just between 0 and 1, the UV values?
That's a good question. I don't actually know the answer to it. I know with normalized device coordinates, at least everything I've read, that's always going to run from -1 to 1 on both axes. But that's for like the screen that you see. And then
Mm,
as far as like the UVs on objects, I know on quads they default to that 0, 0 to 1. I don't know how they extend on bigger pieces of geometry, whether they're always running 0 to 1. You probably know, Andrew, or
Plug in
somebody.
something larger and see. I've been
Um,
encouraging people to try and break this all the way through. Mess with the
oh, break it.
variables. That teaches you, nothing teaches you this stuff better than just putting in weird variables and seeing what it does.
Um, I don't know how to break the UVs on this one. I just know that the built-in for the quad is going to be what it is, which is that 0 to 1, and you're going to have to manipulate that 0 to 1 to be. I mean, you can make it whatever the hell you want, right?
mm, okay.
So if you want it to, because in this, where did I stick that math? After I pull this in, it's all arbitrary from there.
Mm-hmm.
The reason that I went with a -1 and 1 is that um, ultimately I want this camera to align perfectly with a real world or real Godot object, such that when you're exactly where the camera is, that object is exactly where you expect it to be. So the
Mm-hmm.
advantage of aligning it to that normalized system is that that's the system that the rest of Godot is already running in. So all of the math you do in your ray marcher is already going to line up with math elsewhere in your scene. So that's really probably, I guess, the main reason I would do it, rather than kind of inventing your own space. Because there's other, yeah. Does that partially answer your question? Because I don't actually know the answer to your question of whether there's other built-ins that take you
Okay.
further.
I mean that's great. Question: Does you said you use this for clouds?
You can, and I'm still like learning about that. And um, part of this whole series was to just force me to get through it, and it's been doing it. And so I should maybe pull up a cloud um, fader on like Shader Toy or something. Clouds Shader Toy. Let's see if we can. So these are I'm pretty sure these are ray marched. And some of the times I'll like hop into a Shader Toy shader and I'm like, can I find the ray marcher? Like, do I do I understand this concept enough? Um, I mean, they use the word ray march, so I guess that's the clue. Um, here's the ray march loop for int I equals 0, I is less than 190. So there's that number of steps we were talking about earlier. The steps are incremented one each time. And so I don't know if this is using a signed distance function or not. I know that you don't have to use a signed distance function to ray march. You can define your rays any way you want. I mean, that's kind of the magic of the shader code, is that it's your party. So what I can say in principle how it works, even though I could not actually code it for you, I can at least kind of tell you that what I understand the theory to be is that you would have, and I'm going to draw this in 2D space again because that's, what I got. But say I have a grid of voxels. Boop, 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 boop. I'm going to make a big grid. And this grid represents my cloud. And so I say I have a lot of water particles here, and I have a lot of water particles here, and a lot here, and a lot here, and a lot here. And maybe not so many over there. Maybe they're mostly there. And maybe this is all defined by a mathematical noise function. Or maybe it's defined by a texture. Like, if we're looking here, I'm guessing that there's a texture that's actually defining this cloud because we see a texture there. But if I shot the ray through this, and actually I'm going to change color. I shot the ray through this grid. This ray isn't going to hit any ice crystals, right? So this one's going to come out clean. And then that can just, that won't accumulate any shadow as it travels. Whereas this ray will start accumulating a lot of shadow. So it's accumulating shadow there and there and there. And so say you define each little point to drop you by, I don't know, say it drops you by 50%, then just hitting 3 points on the grid would be enough to darken it out completely. So that, I think, is the gist of how ray marching with clouds works. And if I'm wrong, then there's probably somebody in the YouTube comments who will, slaughter me. But I think that's kind of the idea. One of the ways of doing it. Was that an answer to your question?
Yeah, cool. Where can we access this code, or is this private repo that you have?
The code that I did today?
Yeah.
Oh, I think I'm just gonna give it to Andrew to attach as a comment to the YouTube video. How
sounds
do I?
great.
Yeah, and then that way people on the YouTube video can just paste it in. I assume, does YouTube allow that? Like, just
If it depends on length, and if not, I'll link to something on the website where people can find it.
yeah, I did try to put in. I mean, obviously, this is like you can't really declare ownership over this kind of thing because you're borrowing from, obviously I'm borrowing like like a ton of stuff from Inigo Keyleth, and then I'm like patching in other stuff, and then it's got my own kind of weird naming conventions that make sense. But it's ultimately not that long to make basic shapes, and I was trying to make it as short as possible just for learning purposes, because I didn't want like the first ray marcher anybody touched to like just be mind-blowing, because whenever I like open up the ray marchers on Shader Toy, I see this and my brain just like implodes. So I I did not want that. So ideally, if I ever get a cloud shader, I will try to make it the equivalent of like the thing I just did and make it like super basic. But that's assuming I learn clouds.
All right, Elliot and Tyler, anything else from you? Again, those in Discord always get first shot at questions. All right. Ron John KC on YouTube asked what apps you used. I told him Godot and Blender. There wasn't anything else you used, was there?
I used Godot. I used Blender. I used Shader Toy to like experiment with stuff, and that Shader Toy is a website, and the language is a bit different, but not very much. And so I would encourage you, if you're learning shaders, to just kind of experiment with the different places, because I think Shader Toy is like a more conventional language, and Godot makes it. I will say Godot is easier. So if you're like looking for just like what is the easiest place to write one, Godot is going to be easier. The only advantage of Shader Toy, well, there's a big advantage of Shader Toy, which is that there's a lot of like tutorials about Shader Toy. So if you want to follow those tutorials, then you'll have to learn the differences. But I do. I have learned quite a bit from talking with the AI chatbots, and they're interesting when you ask questions about ray marchers. They spill. I mean, to some degree, it was an exercise in like mania, because they would just spit out a lot of unusable stuff, and to some degree, like fixing it and making it work taught me a lot, because it would come out broken, and like the act of like unbreaking it was really informative. Something that they do really good at, though, is help you like translate between things. I mean, they'll still screw it up for sure, but like they at least get you like 50% of the way there, which is better than you were before. And then there's going to be YouTube tutorials that'll help you get a basic shader out. And I'll let me see. I think I have the name of another person who do I have it? Yeah, I don't. I'm sorry. I'll add it to the I'll give it to Andrew. I'll just try to get a bibliography to Andrew of some of the YouTube videos I liked about shaders, because we should totally link to Freya Homeware's series and maybe a couple others.
Killer Nick 01
Did I answer
commented that another person to look up on YouTube for graphics programming knowledge is Acerola, Acerola. He has some really interesting videos on how this stuff works.
Oh, on ray marching or just shaders, or what
Killer
was
Nick,
the
which is it? On how what stuff works, 3D in general, or ray marching, or we'll give him a minute to see if we get an answer. No, that was good stuff, Alex. Definitely appreciate that. Definitely made it a lot easier. A lot of this stuff is brain numbing when you try and understand it. And things like normals, just when you think you understand it, you find out there's a whole nother layer you didn't understand. So, yeah, I mean, you start thinking normals, that's just how light reflects off surfaces. And no, there's a whole lot more to it.
Give a very brief preview of what I'm going to try to do next time in 2 weeks.
Well, Killer Nick says shaders in general, but he also did water and ray marching.
Okay, yeah, water and ray marching. I mean, water is super fun. I had to this is me playing with a water shader. If you can get a ray marching shader going, you can totally get a water shader going, by the way. Ray marching is like way worse. Next time, I am going to try to talk more about, or I'm going to focus on having this align with the camera. because I use that magic 1.3 number to line it up with the camera, but I want to keep lining it up with the camera more, and I didn't fix the aspect ratio yet either, because the premise is that we want this thing to be like a kind of gel that we shove on top of our camera so that as we move through the scene, it's not interfering and it's adding to the scene in the way that we want. And then I think in the future sessions, don't know if I'll get to it in the second one, is to have an object that gets tied to the ray-marched object, so that as the object in Godot moves with the physics, or maybe it's moved by the player, we would want that to be sucked in as a uniform in the shader here. And how to do that is a bit of a party. And that's, for next time. Oh, and one last thing, if you notice, if you're like, why is this constant? That was on purpose just to prevent, if I define these as a uniform, which is how you probably normally do it, it'll get put into your inspector in Godot, and you'll go to change the numbers and then nothing will happen and you will think that you are crazy. I thought I was crazy. But really it's the inspector taking over the uniform on your behalf in the inspector panel, and it's expecting you. Here, I'll go ahead and do that just so you can see what happens. Uniform. Let's see if it shows up. Yeah, so see how light direction appears, and I could start changing that. Say I wanted to change it to 0, I'd move the light by just changing it in the inspector, and I could reset it with that click there. But if you're just trying to get the code to do what you want, start just by making it a constant so that you don't nail yourself that way, and then start converting things to uniforms when you want them to be accessible in that way. That was my preview, Andrew. I think I'll leave it to you to sign me off.
All right.
Killer Nick, but thank you, by the way, for hosting me.
Yeah, Killer Nick says after all, started in Unity, but he's worked on moving to Godot this year. So a lot of folks are making the move to Godot, so this is very valuable. A lot of folks looking at the Godot editions, and I love the lead into what we'll be doing March 16th for the next one. We have time to join the GGDA, so you too can be in the Discord for direct access to our presenter. So March 7th, SimFest, March 14th to 15th, Atlanta Science Fiction Fantasy Expo with Siege sessions. And then March 16th, back to Godot. No more waiting. Alex, that's great stuff. Really appreciate it.
Thank you so much.
And we'll go ahead and
thanks, Alex.
You all can hang out in Discord if you want me to go ahead and kill the stream, if you want to ask other questions.
I'll chill for a minute in the Discord if you want to kill the stream.
All right, everybody. Yeah. Thanks for joining today. We will see you at all the stuff coming up. We'll be streaming SimFest, but come on out anyway. We will not stream Atlanta Science Fiction and Fantasy Expo. Bandwidth is rotten there, so come on out to that event. It's free in any case. And, of course, then be back in the Discord on the 16th. Take care, everybody.